From the mists of time, a legend emerges. The legends of LambdaConf. In this realm of code and sorcery, the unicorn sigil shines bright, guiding the way for heroes true, who gather to share their might. Join us now, brave adventurers, as we embark on this quest. With speakers wise and challenges bold, your skills shall be put to the test. So step forth, ye valiant coders, and let the legends of LambdaConf unfold.
Perfect. So thank you everyone for joining the Legends of LambdaConf, the new series that will be leading us to the conference in 2025. And our first speaker is François-René Rideau. He will be talking about prototype object orientation functionally. This is his extended version of the talk that he gave in May at LambdaConf. So we're very eager to hear it. Thank you so much for being here. One question that I have, Francois, for you, because you're obviously the legend of LambdaConf, how many times you attended LambdaConf?
I think I attended every time since 2016, which must have been the third, maybe LambdaConf, I don't know. So, yeah, LambdaConf is a bit like family. Like it's a great place with great people. Really, and I like LambdaConf has a great positive spirit. That is, it's people who want to understand things, to make things happen, not just understanding things or not just making things happen without really understanding it. It's like the confluence of the two, always a spirit oriented, like towards the future or towards making things happen. I love that. It's great. It's a great place to be, and great people, great spirits.
Awesome. Thank you so much. And thank you for being with us for so many years and for being the real legend of LambdaConf. And welcome once again. Good luck with your talk. We'll be here, myself and Christina, at the end, folks, or yeah, at the end. Let's do the QA in the end. When you finish the presentation, it will be easier to distribute the questions. And yeah, let's begin. Thank you so much.
Excellent. Hi, so I'm François-René Rideau, and I'm going to tell you about prototypes or object orientation functionally. It's a talk about object orientation, but for people who know or familiar or like functional programming. And one of my theses is that object orientation is trivially a subset of functional programming. It's not opposite to it or rival to it. It's just a small subset of it. And it's a subset that can be defined in essentially two lines of code, which is two functions, build and inherit. And with that, you have object orientation. And of course, you can do more things to have more and better and more features to your object orientation. But with these two functions, you already have the kernel of all object orientation. Okay, so let's look at the plan of this talk. We have many parts. Some of these parts I had to skip last May in LambdaConf because we didn't have time. Hopefully, I will have time today. So let's start about OO against FP. As long as I've been on the internet, there were flame wars and battles between object orientation and functional programming. I was on Usenet back in the days, and you had the greatest minds who would ever debate each other, who would debate questions like that. And they were already talking past each other. And if you look at the YouTube today, or look at academic books today, courses, you have plenty of people who are specialized in OO and tell you stupid things about functional programming, really stupid things. And a lot of great academics write wonderful books about functional programming and say not so intelligent things about OO or Inform or whatever. They just don't understand it. And of course, people say that this functional programming is for academics in ivory towers who could never program a real program more than a few thousand lines of code. And that objectionable, disoriented programming is for industrial workers who couldn't reason about a program to save their lives. And Richard Gabriel once wrote an article about paradigms of programming languages and said that sometimes people talk past each other because they have incommensurable paradigms. They think the world in one way, and others think the world in another way, and sometimes they use the same words, but they use the same words with totally different connotations and totally different meanings So they don't even understand what the other say. What the other says sounds totally absurd to the other because they can't fathom that there is a gap in the way they think. Okay, so, and yet in practice, we have peace, we have O and F. If you look at most modern programming languages, they have adopted some of both. You look at C++ now has lambdas. C++ was a poster boy for object-oriented programming for a long time, and then Java, and Java also has lambdas now. So the top, and of course, JavaScript, well, is it functional programming or object-oriented programming? It's both. The most popular language has both. OCaml has objects. The O in OCaml, like everyone knows, stands for how much interest they actually have in object-oriented programming, but it is object-oriented programming. Haskell has type classes, which is kind of 75% of object-oriented programming, we could say, and so on. So, and of course, Lisp had both functional programming and object-oriented programming since the mid-70s. So the two are obviously compatible. They work great together. Everyone enjoys from having both. It's only a shame that OO don't embrace FP more and that FP doesn't embrace OO more. And I will argue even further that since functional programming is my tribe and probably is your tribe if you attend LambdaConf or watch LambdaConf seminars, there remains to understand what is OO. So, okay, so let's admit we are functional programmers, or at least we understand functional programming. And let's admit we understand that there's something about OO. Maybe it's not what the OO pundits say. Maybe they are inarticulate indeed, and they can't speak anything clearly, and what they say doesn't have sense. And yet, there is something that, whether the explanations about it are good or bad, there's something there that matters. So let's elucidate it. And what best way to elucidate it than express it in terms of functional programming? And maybe after we've done that, we can expand our paradigm. We can change how other people think and convince them that FP is interesting. But maybe we can, as FP functional programmers, expand our paradigm and understand at long last what these OO people were trying to say and enjoy the benefits of this understanding the way we can and they can't. So I wrote a paper for the Scheme Workshop in 2021. And in this paper, I explained why OO matters, but I didn't delve into it. It was incremental modularity. I also explained what OO is. I gave the constructive semantics in functional programming of several OO systems of increasing functionality, increasing sophistication. And along the way, I demystified several fundamental concepts of OO. And we'll discuss that soon. But for instance, I argue that classes are not fundamental in OO, and mutable objects are not total fundamental in OO. Actually, the opposite is true. Prototypes are more fundamental than classes, and purity is more fundamental than mutation in OO. And I can prove it. So now we discussed why OO and why FP and the relation to the two. Let's discuss what OO is for. And before we discuss what OO is for, we must discuss what OO is not for. I already argued that OO is not about classes. How do I know? Trivial to prove. There are plenty of OO languages that don't have classes at all, and yet they are obviously OO languages. Actually, the first language that had inheritance that I know of after Simula was a system in Lisp called Director, I think, that had inheritance and had no classes. So there. And the first system that had multiple inheritance, as far as I understand, is also a system from, what was the name? A system written on top of Smalltalk that had no classes, or at least it's the one that introduced prototypes. And so there. So some of the very first OO languages that were not Simula, and Simula had the first arguably OO language in 67. No one else had inheritance until 76, if my researchers are correct. So the very first OO languages, some of them had no classes. And JavaScript, the most popular OO language today, for 20 years had no classes. It was still OO. So obviously, OO is not about classes. Doesn't mean that classes are not important, just like types are important in functional programming, and yet types are not fundamental to functional programming, because you could have functional programming without types. Indeed, if you read the original papers about lambda calculus, there is no types. Types come later. And of course, our languages such as Scheme, Nix, JSONet, plenty of languages that are obviously object-oriented, no, functional programming, and yet don't have types, certainly no static types. Okay, so classes are important, but not fundamental. Class to OO, just like types, are important, but not fundamental to FT. Similarly, encapsulation or information hiding. Well, it depends what you mean by that. But if what you mean is that your language needs to have private versus protected versus default versus whatever public after each declaration, that's not at all what OO is about. Actually, you have plenty of O languages without that. Smalltalk does not have that. Lisp does not have that. This is not essential to OO. If what you mean for encapsulation and information hiding, it's a more abstract level, we're just talking about modularity. Okay, then yes, modularity is actually very important to OO, I will argue as much, but modularity works just as well for functional programming or anything else. It's just programming against an interface. And since you can have modules in SML without OO, that's the proof that that's not what characterizes OO. So there. Inheritance versus composition. In lots of those flame wars and back in the day on the internet, there were people to say, everything that you can do with inheritance, we can do better with composition, or everything you can do with composition, we can do better with inheritance. And this is, of course, absolutely stupid debates, since the two are separate concepts, and therefore will apply to separate sets of disjoint, no, not disjoint, but distinct sets of situations. So it does not make sense to not even begin to make sense to argue as one against the other. That's kind of profound stupidity from those people who say that. Mutation everywhere. Everyone says, objects. I know objects. You need to set fields, and there's mutation. Objects is equate object with basically imperative programming. And of course, there are languages without that, like Nix, JSONet, the object system is built in Scheme. They don't have mutation in them. So obviously, you don't need mutation to have objects. There's plenty of objects in the application. Historically, there was mutation everywhere in OO, but historically also mutation everywhere in FP. The first FP language were what? Lisp. Lisp has mutations if you wanted. So once again, mutation is a bad criterion for OO. And finally, last but not least, message passing. So Simula was invented as some kind of asynchronous message passing mechanism between processes, and that's the language. That's what they wanted to add to Algol. And then Actors at MIT was also based on asynchronous message passing. That's the other things that evolved into OO. Like Actors did not have inheritance at first or OO, but it had it by the late 70s, early 80s. At least Actor systems had. Alan Kay famously declared that asynchronous message passing between concurrent entities was the inspiration for Smalltalk. He declared it, he said it, and yet there is no asynchronous message passing. No, there's message passing, but not asynchronous at all, and no concurrency whatsoever in Smalltalk. And so, even though it might have been an inspiration, that's not at all what OO is about. There's one popular language and only one that uses asynchronous message passing between concurrent entities as its paradigm. It's Erlang. You can also count Elixir, which is kind of a skin over Erlang if you want. That's one language or one ecosystem that does it. And they don't call themselves object-oriented programming. They call themselves concurrency-oriented programming. And the authors have acknowledged, there are interviews where they acknowledge, yes, this is kind of related to OO, but it's still different. And OO people don't recognize Erlang as an OO language. Erlang does not recognize itself as object-oriented. Therefore, message passing everywhere is absolutely not what OO is about. And those who tell that also show their ignorance, and that's sad. So what is OO about? Ta-da! OO is about what I would call modular incrementality, intralinguistically. What does that mean? Modularity is the ability to write programs that may be potentially large programs while only having to reason about a small part of the rest of the program at once. So you want to be able to write a large assembly of software and focus on one part of the software that I will call a module. And for every other module that you want to talk to, you want to not have to understand the entirety of the module in semantics, but only a small part of it that we'll call its interface. That's so when people talk about information hiding and what else was it called? It was called encapsulation and things like that. What they really mean is modularity. The fact that you can write code that will interface with other code, knowing only this teeny tiny part of the other code called the interface, rather than the whole of the other code. Incrementality is kind of complementary. It means that you can contribute modules or increments of software that are as small as possible. If one language forces you to rewrite the entire data structure every time you make a change, it's less incremental than the other. So if you open your classic book by Okazaki about pure functional data structures written, I don't know if he wrote that in SML or whatever it is, every time he has to change a small thing about a data structure, he has to rewrite the entire data structure. And because he only gives you the fundamental things and he skips deletion, it still fits in a page or two. But imagine that you want to modify a data structure and you already have hundreds and hundreds of functions, and you need to write everything from scratch. This does not scale. So this is not incremental. If, on the other hand, you could write your data structure so that you only have to change like a couple lines, like say 10 lines every time you add a feature, that's incrementality. And then, oh, I'm going to inherit from my data structure and add that. And finally, it's about doing it intralinguistically. What do I mean by intralinguistically? Well, you could always take your source files and modify them and say, oh, here I made an incremental change, it's modular. Yes, but it's not inside the language. You have no notion inside the language of the fact that you made two copies of the same file and modified it. Similarly, you can have modularity in C with the very notion of file. There's no notion of modules in C, and yet you have several files that have external or static things, so that correspond to public or private in OO if you want. But there is no actual notion of modularity in C. It's just extra. It's your programming language tools that implement the modularity. There is no notion of modularity inside the language. So you want to have something inside the language that objectifies, reifies, embodies those modules. And so why do you want that? You want that to organize your software development in a way that supports division of labor. You want to be able to write much greater software than fits in anyone's head, because we're not all Edward Kmet or Richard Feynman or whoever is your favorite hero of understanding big things. We can only understand very small things. At least I know I can only understand the small things at a time. So by having modularity and incrementality, we can hope to write much larger software than we could alone without them. So how does OO work? It works within two complementary techniques, I would say, called ad hoc polymorphism, which in modern FP terms could be equated more or less with existentially quantified types, which means that this set of functions do something introducing some type, but this type will be opaque for us, but I know that I can access it. So I don't need to introduce the type. The type will be introduced by the function that I use as I use it. There is also, and very importantly, a technique called, in modern terms, open recursion, which means that you will have some kind of operators that describe a type in terms of itself or some data structure in terms of itself. And so you have say a list is a unit or a pair of a datum and a list. And so you have a recursive definition of list, and the operator that tells you, that takes a list as a parameter and says, given an object of type L, give me an object of type 1 plus A times L. This operator is an operator. And the trick of open recursion is to consider these operators before you take the fixed point. The goal of this operator is that, to get the list, I'm taking the fixed point of this operator. Well, with open recursion, okay, maybe you want a fixed point of the operator, but let's not compute the fixed point yet. Let's be able to compose those operators and do something to these operators before we take the fixed point. And that's the trick of OO. And of course, you want these operators to be first-class entities, that is, to have an existence within your language, or sometimes you're satisfied with second-class entities. For second-class means they do not exist at runtime, they only exist at compile time. So in a sense, you have a staged language. You have a language at compile time and another language at runtime, and these entities, these classes, or these whatever it is, only exist at compile time. This type, for instance, only exists at compile time. And so it becomes a way to factor software. So before we're talking what it is for, we're talking about arranging or organizing software development. And when you look from the inside view of OO, it's how we factor the software itself. And the modular incrementality corresponds to having some kind of impressionist stroke where I'm going to write my software a little bit at a time, small bit here, small bit there, etc. That's how we write software. So what does it look like? I don't know if this is very visible, but this is a typical type hierarchy where we start from top, which is a top object or the top type or something, and then we define something called a tree. And so a tree can be a binary tree, then we refine the tree into a binary tree. But to the right, I also have it. A tree can be keyed by integers or keyed by something else, by reals, by strings, but whatever you want. And my binary tree can further be balanced. The balanced binary tree could be, for instance, a red-black tree or AVL tree. And if I have a tree that is both at the same time an AVL tree and integer keyed, it's an integer keyed AVL tree, for instance. So you can have hierarchies, which are in this case DAGs of specifications, where every specification adds a little bit of information to the thing. That's what OO looks like from a very high level point of view. Okay, so now that we understand what OO is for, what does that mean in terms of functional programming? Can we have a minimal OO model of functional programming? Now we understand what it's for. How do we model it minimally? So this OO is about specifying software in these small incremental modules. Let's call target the software that we're going to specify. So a target will be a data structure or an algorithm or a combination of data structures and algorithms, something that we want to specify. And I will call a spec a modular incremental specification. So the thing that does the specification, the target is the output, and the spec will be the input. So what do I want to do with the spec? Well, I want to build it. So I want to start from some kind of empty canvas, from empty scaffolding or whatever. I call that the base. And then I want to take a spec, and then I want to obtain a target. So I have a function, let's say function build, that takes a base and a spec and returns a target. So that's the minimal thing I want to do with a spec. But the fact that it is modular incremental, I want to somehow be able to combine those many specs together to give a new spec. There are many ways to say you could take a list of spec and return a spec. But for a functional programmer, of course, the simplest way for a functional programmer to do it is with a binary composition operator that we'll call inherit for historical reason. So inherit will take two specs, a spec and a spec, and then return a spec. So that's inheritance, the simplest form of inheritance for a functional programmer. Okay, so of course, in functional programming, everything has to be a function. So if my specs have to be a function, then obviously the output of the function has to be the target, because what will return the target? Well, all I have is a spec. So to build a target, the spec must be a function that returns the target. Okay, what are the inputs of my spec? Well, the incremental aspect means I want to start from something that is partially built. So I want to, my canvas, I want to take a canvas that is partially painted and add some new strokes to the painting. So the first argument to embody modularity will be a partial target. It will be my canvas partially painted. And I will call this the arguments, the things that are inherited. You're given a canvas, that part you inherit, and you're going to add strokes to it. So that's incrementality. So first argument, target, a partial target. The second argument that embodies modularity will be the complete target, the finished product. You want to be able to refer, or this is your future reference, if you want, to the complete product. Here's I'm going to paint the house, and when I paint a house, I'm going to paint the walls, and I'm going to paint the doors, but the doors somehow refer to the walls. Oh, I want a door in the middle of this house, something, or I want 2 evenly spaced windows between the door and the outside wall. You want to, and I want my 2 floors to be of the same height. You will want to have, when you specify one part of your house, has this part refer to other parts of your house. When you write one part of your data structure or algorithm, you want to be able to refer to other parts that will be specified by other partial specifications. So to refer to this part, to the other thing, you will pass something that embodies a modularity, and that something is a reference to the finished product. Okay, and so the specs as functions we call mixins, and yes, the thing I needed to add is that a mixin is typically expressed as a function, then function from super and self to something that extends the super with new definitions. So super corresponds to the part that is inherited so far, and self corresponds to the reference to the finished product. So my mixins, my function, my simplest way to specify software incrementally and modularly will be functions from a super and a self to something that extends the super with new aspects. Okay, so how do we type those mixins? So I offered a preliminary type. Oh, it's a target to target to target. But of course, there are problems with this naive typing, which is that my inputs 1 and my outputs are partial targets. If I give you a canvas that has only no strokes or only a few strokes, it's not a full target. If my data structure that I want to build has X and Y defined, well, I want the whole point of incremental specification is that I want to specify something that only defines an X, or something that only defines a Y, and that doesn't define both X and Y. And therefore, the type invariants for the incremental, for the partial targets are not the same as the type invariant for the full target. And an easy way out, of course, is to use dynamic types. And the way people typically implement objects or object orientation is with, oh, let's have my target type be a string to any. So I have a string that we'll call a method, and any will be the body of the method, or the return whatever value of the method. And so, yes, it is kind of dynamic typing. It gets you out of the problem, and that's what most simple OO systems use, and that's perfectly fine. It works, but of course it can be unsatisfactory to the static typer. So if you really like types, you may want to do something like a mixin takes 3 types as a parameter: the inherited, the reference, and the defined. And you take as input a first, an object of a third type is the thing you inherit, and then take the things that you references, so that's the self, what are the parts of myself I will reference, and I return something that has both the inherited aspects so far and new defined aspects. So that's what your type looks like. And if you want to make it more modular, because this type assumes that you know exactly in which context you will use your mixin, so what it will be composed with, and so you know exactly what inherited is. But if you want to say, oh, my mixin works, I'm not interested just in single inheritance where a mixin is defined and used immediately, but I want to have a mixin, oh, this is mixins, add a new field X, but it can add the new field X to anything, not just add a new field X to something that has a mixin field Y. Then you will want to quantify over what the super type is. So let's assume that super is a subtype of inherited. And then I have something that goes from super to reference to super undefined. And you can refine types further because these types give you the intuition of the incremental aspect. But these types actually fail to give you the proper intuition of the modular aspect because there's a fixed point involved. And therefore, the type that you inherit depends on the final product. So inherit is actually has to be parameterized by self, and reference has to be parameterized by self, and defined has to be parameterized by self, and everything has to be parameterized by self. And there's a fixed point involved. Things get messier, but that's good first approximation. Okay, so I need to rotate my screen again. So what are the minimal kernel of functions for my mixin? So let's assume this simplified type for now. And my object to build my mixins, I will take a base object of type top, where top is a top type for my target objects, like empty objects. And then I will take a mixin that is a complete specification in this case, because I'm trying to instantiate it. So now I need the specification to be complete somehow. And the way to instantiate is just take a fixed point. So I take the fixed point of the mixin applied to my base. That's simple. And similarly into inherit, I take two mixins, and the first one has I1, O1, D1 as inherited reference and defined types. And the second one has I2 inter D1 as its inherited types, which means that the second mixin can use the things defined by the first mixin in its definitions. So there's a sequential, you can use what was defined before, so things do not commute, and the types just work magically this way. And of course, the definition is the only definition that works this way. It's you take a parent, a child, a super, and a self. So parent and child are mixins, or specs, whereas super and self are targets. So how you get the partial. So you start by applying parent to super and self. That gives you a new partial canvas, and then you apply the child. So first you apply the strokes of the parent, and then you apply the strokes of the child. That's what it says. So that's simple enough. And these definitions, the body of these definitions is exactly the two functions I gave you at the beginning of this first slide. So indeed, with those two functions, you have object-oriented programming, you have specs. So is it actually object-oriented programming? Let's see. So usually you say, I gave you something that doesn't even have methods. Like there are no methods involved in my build and my inherit functions. Where are the methods? Where are the values, etc.? Usually, you use a key value record. So that's why I told you usually a target is a string to any. But these definitions work in many contexts, not just with string to something. So a record is often considered as a product of index type. So it's a dictionary mapping string to a dependent type, not any, but a type that will depend on that string. So that string usually fixed at compile time. And the value and or the binding and or the name is of the binding to your string the binding of string to value, or either the name, the labels, the string labels of your key value records, or sometimes the key value pair, or sometimes the value, depending on the context, are called method or attribute or field or var or slot or property or member var or member whatever method. Every OO language seems to find a different name for that. It's very annoying, but I will adopt the word method just because I'm a Lisper, and historically in Lisp it's called a method. And since Lisp may have been one of the first, I don't know how Modular called them initially, but anyway, Lisp was the first language outside not modular, similar to implement OO and inheritance. So method it is for me. And so you can have, of course, records without OO. You can have key value mappings without OO. And most languages that have hash tables or associative arrays or whatever they call it do not necessarily have OO. And so this is largely orthogonal, but yes, let's implement that in FP. The whole implement a record. A record, the top function, the top record, the empty record is something that you give it a function that given anything, given any labels, return an error, returns bottoms out. And to construct a record from a key and a value, and the rest of the record, well, have a function that takes a message as parameter, and if the message is equal to the key, then you return the value. Otherwise, you pass the message to the rest of the record, and there you go. So basically, you implement your record as a lambda encoding of the record query, of the record lookup. And if you use these two functions above, then a point can be defined as adding the key value A3 to adding the value B4 to the empty record. And then if you ask what is the value of the label A for my point, it's 3 because of what the lookup does. So these are records. There's nothing object-oriented about this record. This is just an encoding of records, the lambda calculus. And of course, your programming language probably already has some kind of associative array or record or whatever they're called. Okay, so now how do we incrementally specify records? Okay, now we want a record, but with OO. Okay, so here's KV. I call KV this mixin, or KV of keyval will be my mixin to define a record with this key value. So what does KV do? You give it a super and self, and it just add keyval to the super. So how do I add? What is a mixin, a partial spec for adding key value binding to an existing record? That's what it does, and then I can build my same point, my same record in an object-oriented fashion. Oh, well, I'm starting from rtop as an empty object, and I will build from that. And the mixin is just composing KVBA with kving A3. And this is exactly the same as above, except defined in an object-oriented way. Ta-da! So, okay, I can specify records incrementally. But of course, when in my incremental specification, I don't want the value to be a constant. I want the value itself be able to refer to the super and the self. So I want, when I define a method, my method can call the super method, and it can also call other aspects of my object. So how do I do that? Well, I can define a function method. Function method will take a key, a function, and super and self, and my function will basically be the body of my method. So so instead of having val, I use fun of super key and self. Super key is a super method, and self is the whole object, etc. And you may have noticed by this point that all my definitions assume lazy functional programming. You could do the same thing with a explicit lazy primitive in scheme, but here it works so much better by just assuming the lazy. like super key and self itself. Yeah, you want to refer the final object, but if you don't have the lazy evaluation, it will be there's no way to do it without lazy evaluation. But let's say with lazy evaluation, it's so much nicer and it gives you like so much simpler definitions. Okay, here's a special method fudge x that will modify the x binding by multiplying it by a fudge factor defined in a different aspect. So I take the next and self. So next will be the next value of x or previous value of x, depending on how you look at things. So the value defined by the other, by the rest of the chain of partial specs. And I will take the next. So next is the value of x so far. Self is the whole object. Self of fudge is I'm going to query this other aspect of myself defined in some different spec, and I will multiply next by it. And here's a method called mult yx that defines a method p, a mixin, a partial spec, a spec called mult yx that takes an object and will add, that takes a record and adds a new method p and binds p to the value that will be computed from the super and the self, where you ignore the super, and from the self you extract x and y and you take that product. So you multiply x by y and you put that in the method p. So the whole point of these specs is that you are going to write a small definition that takes into account either what's defined before and or something other defined in different aspects of the object and combine it. And this is exactly what you do with object-oriented programming. Okay, so I think I may have convinced you, if you are familiar with object-oriented programming, that this is exactly what you do when you define a method or you define a new class that overrides a method, etc. This is exactly what you do in object-oriented programming, and all of object-oriented programming can be reduced to this. And so with two functions, build and inherit, and maybe a third function method here, we have all of object-oriented programming into 3 functions. Okay. Do I get that out of my ass? Not exactly. The theory of that was written by Gilad Bracha and William Cook. They published about mixins in 1990s. So the theory exists for a long time. The specialists for records only, by definition, also work for arbitrary types for my targets. So I'm slightly generalizing, but not by that much. And the theory was already there, or most of it. In practice, so even though the theory was defined in 1990, we have to wait until 2014 for those exact same definitions, modulo like change of order of self and super or whatever, to be used by JSONet in 2014 and by Nix in 2015. So JSONet is a language, very interestingly, that evolved as a cleanup of the Borg control language. And they decided, oh, this Borg control language is everywhere at Google, also known as Google control language. It does something cool that everyone thinks is cool and yet everyone dreads. Why do people dread it? They dread it because DCL uses only dynamic binding, dynamic scoping. So if you want, all the variables are in the radar monad if you are Haskeller. So it's all side list style bindings. So people hated that aspect of DCL. So someone say, hey, let's invent a language that has a nice modern syntax that is inspired by a mix of JSON and Python, and put a pure lazy functional language on top of it and see what it gives, and have a lexical binding called JSONet implemented in C++. And then independently, someone else, inspired by many papers, Haskell papers, etc., implemented what they call an extension system for Nix. Nix is a package manager and distribution manager for for Linux and Mac and Windows these days. But you can have all your software defined in a pure functional way. And the pure functional language in which you define your software is called Nix. And the extension language of Nix is defined with a semantic that is exactly the same as JSONet, and with an implementation that is exactly the two functions that I gave you, modulo the order argument and modulo the fact that it's specialized for records. So wow. Independently invented 25 years later, that will use the same, essentially the same underlying mechanism, but completely independent because there's a trace of information from one to the other, but reinvented the same thing. So there's something essential, fundamental, and it's only 2 lines and prevented many times and it does the right thing, and people independently find the same thing. So obviously there's something to it. It's a fundamental discovery, fundamental structure in programming language. And of course, there are plenty of less simple and less pure precedents. You could say that the prototypes defined in director in 1926 already kind of had the same semantics. If you squint a bit, you only need to squint a bit to see that all the OO done since the 70s is also the same. And the theory by Cook and others was supposed to model what other people were doing in dirty ways with side effects in other languages. So it's not, none of it is completely by chance. Like people were looking at the same things, and that's the fact. It's not chance. It's an essential structure of functional programming and of programming in general. Okay, so let's go further into inheritance and what inheritance is, because inheritance is the heart of OO. Like if you have inheritance, that is, if you have composition of partial specifications that are incremental and modular, then you have OO. And if you don't have that, you don't have OO. Like if you have only modularity without incrementality, that's not OO. If you have incrementality without modularity, that is, I can define my software by adding a little bit of information. It has a large effect, but I need to know everything that was before me in a modular way. Well, that's not OO. It's called gzip compression or decompression, like writing your software in small bits that define a lot of things. Yeah, it's called compression or decompression. But if you have modularity and incrementality, you have inheritance, and that's OO. So once again, the essence of OO is to have these operators that you can compose before you take to the fixed point. So my specs are these operators, my mixin, my specs are these operators that I'm going to compose. And at the end, after I've composed all of them, I take the fixed point. That's why the sequence is O from not OO. It's if you want to give type to them, well, you need to have very advanced subtyping systems. And since most functional programming languages don't lack good support for such type system, they don't have that. And that's a shame, because good type systems for that have existed since at least early 2000s. There's a great paper by the Fortress team on how to do multiple inheritance and multiple dispatch, etc., in a nice way with subtyping. And there are plenty of good papers, although most papers about inheritance and OO totally ignore the good techniques, and that's very sad. And most books about OO by functional programmers totally miss it, and that's very sad. Anyway, it is possible, and you need to support good subtyping if you want to give static type to your object-oriented things. And importantly, there are historically been 3 flavors of inheritance: single inheritance, multiple inheritance, and mixin inheritance. And here, single, mixin, multiple is listed in order of complexity or elaboration sophistication. Historically, single was discovered first by Simela, and mixin was discovered last by Bracha. But multiple was discovered, like, I think, as early as 79 or 78. I'm not sure exactly when. Once again, the very first Smalltalk prototype object had multiple inheritance. And Cedar, which also West Coast thing from Spark. Spark had multiple inheritance. Flavors on the East Coast, Lisp system had multiple inheritance in 79 or so. Anyway, that's very old. Yeah, you can't say that we didn't know how to do better. Yes, you know how to do better. So mixed inheritance was the last, but it's the simplest form of inheritance given FP. It's for functional programmers. It's really, you don't have to deal with list or with graph or anything. You just deal with two partial spec, you compose them. That's simplest for functional programmers. But historically, OO was not defined and discovered by functional programmers, so they discovered single inheritance first. So mixed inheritance is best for functional programmers because we use higher order functions, we use fixed points, we use laziness. We indeed require more subtypes that most FE has. So that's why most FE languages don't just use this definition for object-oriented programming, and that's a damn shame. You could say, hey, Haskell, there was Haskell defined in 205, and 20 years later, you still don't have OO. It sucks to be you. You should be ashamed. You should hide, and you should implement that and apologize. But, well, I hope the member of the Haskell committee enabled the proper pragma to have that ASAP. Okay, so mixed inheritance is 206. I don't know when 206, who did mixed inheritance when. I know that Gladbacher in his strong talk tells me that they had the mixing inheritance underneath, so somewhere sometime in the 90s. It was not exposed to the users except for reflection, but apparently they did have mixing inheritance. So it's 206, I suppose, is when Racket exposed form of mixing inheritance for its UI and documented it, and it was widely used. Okay, so mixed inheritance, I think the first for FPs and the simplest for FP, but it's the last historically. The first historically is single inheritance, which was when inheritance was discovered by Simula 67. And if we try to mix it, to express it in terms of functional programming, is all about how you do it. Once again, it was for, there were some people in the late 80s and then grown by Cook in 1990 who have definitions like that look like that. So a generator of cells, that's my operator, a simple operator of which I will take a fixed point, they call it generator, function from self to self. To build it, I just take the fixed point, the Y combinator. And to inherit, to create a new generator, you take a generator and you take a mixin of STT. So this is the type of mixin that I had before. And then that gives you a generator of S inter T, the intersection of S and T. So, wow, that means that to use single inheritance, from the point of view of functional programmer, you need to already have mixin inheritance. Except your mixin, you're only allowed to use it immediately after you define it. So this is not a very, from a functional programming point of view, this is not a very nice construction. But historically, it's the first because it's simplest from the point of view of imperative programmers. In Simula 67, they call it a prefix class. And so here I have the order of indeed the generator to the left and the mixin to the right. And so we pass super first and self second. And this is what Smalltalk did not actually have that in 71. Smalltalk had that in 75 or 6, I don't remember, 75, I think. So this slide is slightly wrong. Smalltalk did not have inheritance until 75. So mixed inheritance, of course, is more expressive because basically in single inheritance, you can apply your mixin, but you cannot compose them. And you can only add one mixin at a time at the end of a prefix list. You don't have a notion of mixin independent from your generator where you can compose your mixin. Every mixin needs to be attached to a chain of mixin starting from the empty generator. So this kind of sucks. This is obviously less expressive. Anything you can do with generators, you can do with mixins. So mixins are more expressive or incremental. It's just a better way to do OO. And why does it even matter? Like, obviously, if you have functional programming, you can deduce one from the other, especially with a few higher order functions. And that's exactly how Racket does it, by the way. Racket, it's UI defined in terms of single inheritance class, but then you use higher order functions to define your mixins. And that matters because most OO happens at the type level, and their mixins and generators, etc., are second class entities, not first class entities. In the type level, you don't have full functional programming, and then the difference becomes very tangible because you cannot have full functional programming in your OO language, and that sucks. But if you can have functional programming in your OO language, you do the same trick as Racket. You define your single inheritance first, and you're mixing as higher order function on top of that. So the difference matters because people are not using functional programming. Okay, and there's a problem with mixing dependencies. Oh, let me rotate my screen again. There's a problem with mixing dependencies, which is if I have a mixin O, let's say the empty mixin, object, and define an empty object, and I have a hierarchy like that where mixin depend on definitions from the other mixins. So E depends on O, D depends on O, B depends on O, etc., 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 according to this DAG graph. Well, I could say, well, every time I'm going to define a mixin, I can just define, I can define C, or I can define O, I can define all those mixins independently, but whenever I want to use K1, actually, I never want to use K1 alone. I always want to use K1 and C and B and O. And whenever I use K3, I don't want to use K3 alone. I want to use K3 and A and B and D and O. So if I have to, every time I use K1, remember that, okay, I don't want to use K1, but I want to use all this graph with me. It's a lot of work, and it's not modular, which means that when people, I want to only expose K1 in my interface, but I cannot. I want to expose K1 in my interface, but also A, B, C, and O. And the fact that K1 must be used this particular way. So that's the opposite of modular. It means that my user needs to know much more about the internals of my objects than I would like to expose. So you would say, oh, that's easy. I can just pre-compose. Every
Francois,
time.
apologies for disturbing you. The screen switched, so we can no longer see your presentation. It just moved to the right side. Oh, we can now. Thank you.
Oh, okay,
Thank
but
you
then
very
it
much.
cut at the bottom.
Thanks.
I will have, I'm sorry, I failed to install Zoom on my laptop, and now the presentation does not appear as good on the on this
We can
phone.
see it now quite well.
Okay,
It
so
came back to normal. Thank you.
Okay, thanks for telling me that it wasn't showing. So pre-composing the mixins is wrong, because now if you want to say, oh, I'm not going to define K, I'm going to define K pre-compose with the thing it depends on. So now K2, say, I don't define K2, I only define OE, OD, OB, K2, and export that. The problem is that's totally wrong. For instance, O could erase your object and return the empty object always. So when you do OE, OD, OB, K2, the first O, okay, fine, you define an E. Then you define O again, it erases everything that E has defined. You define D, it erases everything that E has defined. And by the time you only have OBK2 and you have not defined the E and D, and therefore your pre-composition just fails. You can't. So pre-composing fails. Post-composing is too much work. Pre-composing fails. How can we deal with that? Well, the solution is, of course, that you want neither to pre-compose with or post-compose. You want a system to manage a composition for you. And that's called multiple inheritance. So with mixing dependencies, if you change the node, if I'm going to change my node every, if I keep things post-compose, every time I make a change, every one of my users has to see the change and take it into account, and it's very time-consuming for everyone. all my transitive users, because my direct users must change their code, their users must change their code. So you change a small class somewhere in the library, and a whole universe of code needs to be changed. That's not modular. Pre-composing does not work because it's incorrect. So you want to compose dynamically. Of course, if I only single inheritance and not mixed inheritance, you don't even have the problem, because single inheritance is too inexpressive to have this issue of DAG dependencies and multiple dependencies between multiple arcs. So there's yes, when you add a new class, superclass in your inheritance, it's transparent for your users, but that's only because single inheritance is inexpressive. Also know that my precedence list in the list tradition or the reverse order from the similar tradition. The similar tradition has the parent first and the child second, and precedence list often lists the child. The leftmost is the most specific, and the rightmost is the least specific, the most generic. So be careful when you see talks about inheritance, and especially multiple inheritance, which order is which. Okay, so with multiple inheritance, you specify your prototypes, your specifications, and you specify your graph of dependencies, and you let the system automatically linearize your DAG into a precedence list. So it finds the list. So you give it this graph, and it will automatically give you a precedence list such as the one below, and it just works. So it's much more modular and incremental. Okay, so there are bad precedent lists you don't want, and if you have an algorithm that preserves all the properties you want, it will just work. There's a paper from the late 90s, I think, about an algorithm called C3, which preserves 3 constraints of inheritance. So you want, of course, anything you depend on, with your left of the thing that depends on it, and the orders of the precedence list of your parents must be a subset or an ordered subset of the presence of your precedence list, etc., etc. If you have all the good properties, you have basically the C3 algorithm, modulo whatever heuristic C3 uses when there's ambiguity, when there are multiple possible choices, well, it will be fine. Okay, and of course you can combine multiple and single inheritance. A lot of people still use single inheritance because they say, oh, with single inheritance, we can do various optimizations, such as if the index of a method is, if a method is at a given index in an array for a superclass, it will be at the same index of a longer array for a subclass. So various optimizations are possible. And so some people still want single inheritance, and Java has single inheritance, even though it was invented like 20 years after multiple inheritance was invented, etc. But we can have the best of both worlds. We can say, hey, for this class, I want all its children, all the descendants, to have it as a prefix or suffix, depending on how you view left or right order. So I want to be always a prefix of all my subclasses. It is possible. You say, okay, this is a prefix class, and this is not a prefix class, and then you can optimally combine all of them. I implemented that in Jabal scheme. You just need to extend the C3 algorithm with an additional current property, so it becomes a C4 algorithm. And I will note here that in the Lisp world, we call the single inheritance one struct and the multiple inheritance one class. In Scala and in some Smalltalk's world, we call traits the multiple inheritance one and class the single inheritance one. In C++, struct and class are both multiple inheritance, but just one has everything public. So there is no common vocabulary from one language to the other. That's very sad. And you have to be aware of those pitfalls when you read papers about inheritance in general. So there's a lack of common vocabulary. And yet, if you're aware of the pitfalls, it's pretty simple to understand what's going on. But once again, the literature and the communities don't agree on vocabulary. Okay, so we discussed O versus FP. We discussed what O is for, how to minimally model it in FP, what various flavors of inheritance are. Now we are going to discuss objects or lack thereof. Okay. So, excuse me. Right. An hour. Okay. Can I finish this? Okay. So apologies, there was a emergency at home. Okay. So you see that in my talk, I've been talking about targets and about specification, about records, but there are no classes and no objects, only specs and targets. So specs is not a record because a spec is a function from target to target to target. There's no method anywhere. It's generic. It applies to things that are not record. A spec is obviously not a record. A target is obviously also not not an object. So a spec is not an object, not a class. A target is not an object or not a class. There's no inheritance involved in a target. A target is any value of any type whatsoever. It can be. Doesn't have to be even a record, but even if it's a record, there's no inheritance possible in the target. By the time you have the target, you've already forgotten the spec. You've just called the spec, evaluated the spec, taken the fixed point of it, and you cannot inherit from the target. So you have a spec that is not an object, not a class. You have a target that is not an object, not a class. Where are my objects? Where are my classes? Well, that's a good question. And yet, with just specs and targets, I can produce these slides. These slides have been famously produced I use the definitions above, with specs and targets, I produce slides. What does it matter? Look at, well, I can't share the screen of my source code unhappily because I'm presenting from my phone. But look at this plan of the talk. In the source code is just a slide that says include a plan slide and nothing else. And it just extracts from the context the fact that the slide has this prelude, introduction, and that the current thing is in red and the rest. And if you look at the definition, how can this definition include class equals prototype when this section hasn't been defined yet? And indeed, if you consider an eager functional language, that looks like an impossibility. How could you refer to something that has not been defined yet? But of course, if you're lazy, you can just refer to your super and to the self, and the self is lazily defined. It's an argument that gives you access to the entire document, and the entire document, of course, has all the, or will have by the time you evaluate it, all the sections, and therefore you can include you can extract the list of sections and highlight the current one even before the next one has been defined. And that just works because the evaluation is well founded and because you use lazy evaluation. So lazy evaluation is of the essence here, and I use specs and targets. My target is just in the end an HTML document or something that explains into an HTML document, and my spec is just something that takes a self and a super as arguments and can extract from the self the other aspects. So you can define those slides, you can define lots of things, you can do lots of object-oriented programming without objects. How is it object-oriented programming is no object? Well, maybe the word object-oriented programming is a misnomer, and people, when they discovered the original meaning of invention is not something you make from scratch, but something you find in nature, like invention that from in the Latin invenio means I come to that thing, I come into that thing. So inventing is discovering something that already existed if you want. So it was called OO because people didn't understand what that thing was, but it's actually inheritance, and even the word inheritance discussed was the right word, but the essential thing in OO is not objects, it's inheritance. Okay, so I can also have my targets that are not records, but that are something totally different. Once again, it's a value of any type. I can have functions from integer to integer or real to real as my targets. I could have, and I have examples of that in, not on the slides, but in my papers. I can have records that allow, but records are better than, say, functions from integer to integer. If you have a function from integer to integer, how the hell are you going to add side information? So I want to have this function depend, be a projection or simplification or approximation of function from real to real. But if I want to incrementally specify my function from integer to integer based on that function from real to real, where in my function of integer to integer am I going to encode that? Like in my partially defined entities, I want to be able to have aspect, and my total entities, I want to have an aspect for that function from real to real that I'm going to approximate or whatever. And so there's, yes, okay, you could survive with targets that are not records, but records make things so much easier to deal with as targets. Records are objectively more general purpose targets. And so modular extensibility. So you can have a spec. Yes. So when I defined this document, or when I defined in Nix a large DAG of plenty of modules that refer to each other, because this module defined, say, what will it define? A browser, but this browser is compiled with the C compiler GCC that goes with this library that is self-compiled with GCC. So you have a graph of mutually dependent recursive specified objects, and that's, yeah. So the point is, when I define a graph of records that point to each other, which of my records will be extensible and which will not be extensible? And you have several possible answers. You can say none of them will be extensible. And if nothing is extensible, then you don't have O at all, and that's fine, but that's not incremental. You can say everything may or may not be extensible, and I have a bit flip, a mental bit flip for every entry everywhere. And that means that now the type of my objects that I need to understand and remember will get exponentially more complex as I have more objects in my graph of records. So that is totally unacceptable. Like no one can deal with this exponential explosion of things. Or you can say all of them are extensible, or you could say only the top one is extensible. I forgot an option. And that's where you really want to be able to view things either as the record or as a spec that you're going to extend, depending on the situation, depending on whether I'm just using it, or here I'm just using the specification and here I want to extend it. And depending on the situation, I want the same entity to be either extensible or not. How do I do that? Well, I will use a technique called conflation, or an implicit product, or whatever you call it, where you say, okay, I'll define a prototype as the implicit product of a spec and a target. And depending on the usage context, I will implicitly project to the spec or to the target. And then all my entities in my dense graph of record can be implicitly extensible. So this is pure, and right so far this is pure, and because it's pure, every spec has a single target up to observational equivalence that is its fixed point. So if you don't have any side effects in your language, and in this context, lazy evaluation does not count as a side effect, you could implicitly define the target from the spec. But of course, computing the target can be expensive, so you don't want to explicitly recompute it at every point. you want to implicitly have it present. And if you have side effects, then obviously then you can't deduce a single target from your spec. So now you will want to have a prototype in a effectful system. Two prototypes would have the same spec and different targets. So you will want to distinguish them. So, and that is what we have called prototype object orientation. So in prototype object orientation, you don't have classes. You only have these objects that are the implicit conflation of a spec and a target. The spec telling you how to compute the thing after fixed point, before fixed point, and when to do the fixed point, you have the target. And first, once again, the first prototype objects are from the 70s. The ELT scheme in 82 used it for its graphical interface. It's as old as programming. Okay, prototype object-oriented programming. It's obviously simpler than class-based. So an object in prototype OO you call object or instance. This prototype, this product of a spec and a target, and it's a first-class entity that takes at runtime. And yes, it was mutable in director, SingLab, T, self, and JavaScript from the 70s to the 90s. And we have pure versions in JSONnet and Nix. So the pure variants will have only been used in production, let's say, for 10 years. Of course, with conflation, it's not just for mixins or whatever. I mean, you could say a spec is a mixin and a list of specs. That's multiple inheritance. That says my spec is itself the given of the mixin function, and then the thing they depend on. So it's a product of dependencies, and you could add default values. The default values would be a record with the default values, and you can add more and more things and in an implicit or explicit record. So yeah, your spec is actually more than a mixin, than a function. It's a product of many things. And you could have also a no such message handler. You could add assertions that you want to run when you instantiate the thing. You could add types. You should have first-class types or do an implicit product, yet another implicit product at the type level, whatever. You could add more information to your spec and still have the target next to it at the end that is a fixed point or the instantiation of it. And of course, your targets can be more than just a record. You might want a target to define a function, an integer, or anything. So in what they call pure OO, there should be no privilege built-ins. Everything should be accessible as through the method calling or message passing or whatever it is, interface of OO. So you want to have objects that be callable. You can have arrays that are defined as objects, etc. So actually, a target can be more than just a record. It can be a record with an implicit product in conflation with a function, with an array, with an integer, with whatever values you have. So conflation is a very important concept, and actually it's the key to the semantic simplicity and the usability of object orientation. So it is very important to distinguish these two entities, spec and target. If you distinguish them, you have very simple semantics for what it means to compose specs, to instantiate specs, and to deal with targets. And if you don't distinguish spec and target, and you still want to pass around objects that are the conflation of spec and target, but you don't want to admit that you have a product or that you can have so absurdly complex semantics describe the thing if you don't recognize that you have two distinct entities, spec and target, and that then you conflate them together. So conflation without distinction is utter confusion, and I suppose that's why for 30 years I didn't understand object-oriented programming. It was way too complex. You had to carry the two aspects at the same time, as object as spec and object as target, like utter confusion. But once you distinguish the two, all O become super simple, like beautiful, simple. It fits in three lines of code. It's yay. So you can reason about it, and yet the conflation, the fact that the product is implicit, is what gives you superior ergonomics. It's very easy to use a callable function, a callable object, or whatever. It's so much easier than to add layers upon layers of syntax. So semantics can be simple, and the syntax can both be simple if you understand that you have both these products, and yet these products are implicit. Next. Okay, we're almost at the end. So I think we've already seen the essence of object orientation. Now it's application and how this applies, say, to class. Oh, what is class-based? So most object systems are class-based. So what is a class-based compared to what we've defined so far? So Simula 67, Smalltalk, C++, class, Java, C#, Python, all the popular, even JavaScript these days, people tend to use only classes and much less prototypes. All the modern OO languages tend to be class-based, at least superficially. And most people don't even know that prototype OO exists. They're only taught about class-based OO and taught as if it was the only kind of OO that exists. And so, is class-based OO the same? Like, or both, or are they just two different things, or the same thing? Are they the same paradigm? They both have inheritance, but yet, is it? What's the relationship between the two? Okay, and the answer is actually trivial when in retrospect, is that class OO is just prototype OO for type descriptors. So my target is a descriptor for type and associated functions. If you know SML modules, so my target would be an SML module if you want. And my spec, well, it's an incremental modular specification for my targets. And the problem or limitation or whatever of most class OO is that they only allow this at the type level at compile time. So you're not allowed to have first-class objects that are partial targets. You want at runtime all your targets to have been expanded, all your types to have been fully expanded at compile time. But the OO part all happens at compile time. All the inheritance, all the specs, everything will happen at compile time. And you can retrieve kind of a spec and target. Your spec is an abstract class and your target is a concrete class, or a class considered concretely is your type, basically, and that's your target. And if you consider a class, oh, this class, let's consider it an abstract class, or even it's an abstract class that is not meant at all to be instantiated, or it's meant to sometimes be instantiated concretely, but let's consider this class abstractly. And basically, they have to reinvent it, but because they never distinguish spec and target to begin with, semantic is so horrible. Okay, so in class OO, when you call what you call object or instance is not your target, it's an element of the type that is itself the target of your class seen as prototype. So your class is a prototype, which is a second class citizen because the prototype only exists at compile time. And this prototype, if you take its fixed point with the proper base, defines the type. And what you call object in class O is very different from what you call object in prototype O. In prototype O, you call object that thing, the class. But in class O, you call object the element of the class. And that can lead to a lot of confusion for people who try to learn prototype O and they only saw class O or the other way around. Okay, so mutable class O, once again, Simula, Smalltalk. This is a mistake. Smalltalk only had inheritance in 75. So Smalltalk only qualifies as object-oriented programming in my book since 75, even though they claimed the label earlier. They invented, I think Alan Kay invented the word object-oriented like back in the late 60s or early 70s. Flavors in Lisp had it in 1982. Actually, flavors existed in 80 and maybe even 79, I don't know. C++ was published in 85, but I think the ancestors of C++ was C with classes, which also is from 79. So class O is old It's very old. OCaml in a pure, well, objects in OCaml don't have to be pure, but they can be pure. And OCaml exists since 96. Haskell has existed since 2005, pure functional. So you can have class-based OO that is pure functional if you want also. So once again, that has nothing to do with mutable or the mutable class of its own. What's important in class is that class-based is prototype based as a compile time at the meta level, where the only thing you're allowed to have as your targets are types. And so that means that to express that in a functional programming setting, you need to have a notion of staging or existential type or even dependent type, so you can talk about your prototype for type descriptors. And of course, most programming languages have very limited type level computations. That's why the difference between mixin and single and multiple inheritance matters, because, if I had arbitrary type level computations, I could just use higher order functions to define mixin inheritance in terms of single inheritance and multiple inheritance instead of mixed inheritance. But since I don't have this kind of functions at the type level, I can't. And then the inexpressiveness of your calculus at the type level makes the difference between mixin and single and multiple inheritance matter. You could say that a singleton class is a bit like a prototype, but it's much lacking dynamic. It's much less expressive still. You can't recover prototype object-oriented programming from class object-oriented programming. It's just class is just less expressive. Okay, type classes are kind of classes, but instead of inheritance, you don't have inheritance, but you can explicitly call objects from another function from another type class, which means that you're about as expressive as single inheritance, but you also have the notion of multiple despite, because you can have constraints on multiple types. You have type class inheritance. So in infinite, type class is more or less equivalent to class, basically. And it's not an informal more or less equivalence, because I added an automatic translation between two styles of programming in my list interface libraries in 2012. So it's more than an informal correspondence between two. There is a formal and automatic translation between the two styles. But of course, Lisp does not have type inference. So you have to explicitly pass this interface objects, which is the same as in, suppose, in core Haskell. Haskell gets disregard to core Haskell, where you also pass dictionaries instead. So a type class, which is an implicit object in Haskell, becomes an explicit dictionary in core Haskell. So and the two are equivalent. And in the class view, basically, every object carries as a hidden field a copy of its dictionary. And in the type class view, well, you pass the dictionary separately from the value. So that's the difference between the class and the type class view at runtime. And I would add something about, well, go back about class OO. I say that class OO is just prototype OO at the type level. But if you look at C++, so I'm telling all the which for the longest time was the object-oriented language prototype that everyone was referring to. Well, C++ and template programming in C++ is exactly a pure, functional, lazy functional programming language. It's just that this language is only available at compile time in C++. But so all of the object-oriented programming happens at compile time. Therefore, C++ can be seen as a layering of two things. A totally imperative, non-object-oriented programming language like C that is expanded into from a pure functional pattern matching, lazy functional language. So yes, it's more than an analogy. And indeed, I have examples of how you can use lazy strings or whatever as template in the pure functional prototype OO style in C++ at compile time. Okay. What are impure challenges for object-oriented programming? Well, so far, all my examples and definitions were in the pure functional context, but of course, you can also do add the state, etc. If you have only eager functional programming, you will want to have a lazy construct or emulate it with a mutable with mutation, because that simplifies things. Your eager Y will only work with function and targets, and since without mutation and without lazy, there's no way to do sharing. If you have a pure eager Y, you do a lot and a lot of exponentially multiplied recomputations of the same functions all the time. It's totally inefficient. So pure eager functional programming without mutation just doesn't make sense. Of course, it doesn't exist either. Like historically, Lisp had mutation, and that made things worse. So with lazy Y, you can have delayed values. You can have sharing between your delayed values, and you avoid the recomputations. And that reminds me all of a great paper by Blanc-Lévy called by Push Value in 1999, where he explains the duality between values and computations, and that really when you have a partial spec, a partial spec for a target, partial target, what you really have, what you're specifying incrementally is not a value, it's a computation, and the value is only the end result of the computation after you evaluate it. And so in a way, this fixed point with object-oriented programming is essentially what you call co-inductive and not inductive. And that matters in some ways. And that's why if you want to do it at runtime, you have to have all this co-inductive baggage everywhere. And if you want to reason statically at compile time and make it inductive and be able to define inductive data structures, etc., at compile time, that's why you will want to restrict your language. It makes sense sometimes to restrict things to only happen at compile time or happen statically, and you can prove more things when you do statically. There's a point in it. It's not just, oh, they are less expressive, but sometimes less expressivity allows you to make the reasoning about it stronger. So there's a point in doing things only at compile time, but still you have to recognize that you sacrifice something, and that the full extent of OO is only achieved when you have it at runtime. Pure, yes, if your thing is really pure, how are you going to put an identity to your DAG? So I say that multiple inheritance, a spec is a product of a mixin and a list of specs, but that only works if you can recognize that every node has an ID. So maybe you need an ID as a third or another implicit thing in your conflation. And is an ID pure, is it impure? Well, it's a kind of effect that if you do it right, cannot be observed or can be observed in the right way. So you can view it just like as pure as lazy evaluation. One man's pure, obviously, another man's pure. So you want to be able to compare. That's one of the things that makes multiple inference in Nix not work so well, because you don't really have pointer equality. You don't have pure node equality for your DAG in Nix. So multiple inheritance will require you to either have explicit labels that you manually curate, that's not the modular as it should be, or uses tricks that may or may not work. Of course, you could try to put all your O in a state monad or whatever in some kind of monad that generates your tag. This is the usability. It becomes unusable and not backward compatible with existing Nix style. You could use explicit label, as I mentioned, that's not modular, but modular enough if you have a strong convention to maintain them. And of course, a convention can be seen as moving your computation from software to wetware. So, one man's pure is one man's pure. If you have actual stateful side effects, then you have multiple potential targets for same spec. And so you have notions of cloning. Hey, a cloning is just take the same spec, but computing a new target for it. And the question is, when do you share or not share the variables, the element, the cell, the mutable cell? What happens if you dynamically modify your super? Some languages allow that. I know that in Self and Smalltalk, they maintain a list of all the instances of a class, that if you modify the class, it does the right thing. And if you modify the super list, it will also do the right thing, etc. This is lots of bookkeeping. Your language may or may not want that. It's an option. But when you introduce side effects, then there's a whole universe of extra semantics that you need to deal with. So it's much more complex. It's also more richer, and you can find more efficient variants in it that satisfy you. But there's no denying the much extra complexity that comes with side effects. You can also try to see, what if we have side effects, but only in the pure ways for linearity, etc. And yes, but enforcing linearity, either statically or dynamically, is very hard and costly to enforce. In class-based OO, like C++, of course, all the O happens at compile time where everything is pure, so that's fine. So actually, even in C++, object orientation is pure functional. So people say objects are mutable object. No, object is always pure functional. There's not a single class-based object language that is not pure functional, except for reflection. Okay, but you say that reflection is the main thing that Smalltalk has for objects. Okay, so maybe Smalltalk and Self have an endless set of reflection are not pure functional for their OO. Even less need to do reflection. Okay, but mainly OO is a pure functional phenomenon. And of course, caching, if you add more caching, you can share more stuff, but the caching validation becomes hard. Okay. Another thing that's pure, not pure, that's very interesting is the notion of multi-methods or mutually recursive classes or friend classes, or in Haskell, they have the notion of orphan type classes. And is it pure? Is it not pure? Because that means that when I define a new definition, it can modify retroactively the definitions of other things that existed. So and that's a hack. You can, in a pure language, to deal with orphan type classes, I'm going to side effect a global table of methods and hope there is no conflict. And that means that your Haskell is actually not as pure functional as you'd hope, because there are these orphan type classes things. Or you can try to prohibit them then, but there are lots of good things you want that become prohibited. And of course, that's just a pure functional solution. And this pure functional solution was also discovered by Nix and used by Nix everywhere. And the solution is that the open loop is global. In Nix, everything in the end takes PKGs, which is a top level self object, as part of the open loop on which to do recursion. And in my document, I have a self object for the entire document, and that's how I can get access to the table of contents, etc. And every node points to the upper node in my hierarchy, so I can always get not just the table of contents from my current level, but for all the levels, etc. So the next solution is that, how do we deal with these mutually recursive classes? No, actually, we don't have multiple recursive classes. We have a one recursive definition for the top DAG. We have a self-recursive universe of classes, universe of modules, universe of things. And that change your mind, woo, oh, wow, I'm not, the difficulty disappears, but now you understand, wow, that you have a much bigger universe. You also understand that yes, you understand that since the thing you take the fixed point of is not a class, but the whole thing, what you curate not one class, but a library of classes, entire namespace of classes. It's not individual. You stop thinking about individual classes. You start thinking about ecosystems of classes and ecosystems and libraries of object classes, types, whatever you have, modules, packages. what they call that in whatever software. Okay, so we can do more things with functional ways. We can generalize methods with optics instead of having a method that is just a direct member of a record. Now, since we have a hierarchy of classes and a hierarchy of hierarchies or whatever, I want to access the sub method of this sub-object, whatever. I can define things like before, after, around methods, aspect-oriented programming, advice, class. I can all do that in a pure functional way. My method combinations can also be done in a pure functional way. So all these things that a lot of people skip when trying to define the semantics of object orientation become accessible if you use just simple lenses and other functional programming techniques on top of the framework I propose. So if you want to do things like that, you're welcome to help take one of these things and make it happen. But yeah, it can all be done in a pure functional way, and so much better and safer and with nicer semantics than done without FP. Okay, so conclusion. My conclusion is that I have this teamwork check paper where I explain why OO matters, why it's incremental modularity, what OO is, and I give, once again, the constructive semantics in FP of several object-oriented systems, including sophistication. I demystify some fundamental concept of OO and show that prototypes are more fundamental than classes, and purity is more fundamental than mutation in the context of OO. Incrementality and majority have to happen intralinguistically inside the language. That's what's the key concept of OO. My Meta-Thesis functions are made to be composed, not just applied. That's what makes the beauty of Mixin inheritance versus single inheritance. And then we can make it modular with multiple inheritance. Conflation is the key to simple semantics. It says that a prototype is a spec, and the product of a spec or target, or prototype for a target is the product of a spec and the target. Class is just a prototype for a type. And why did I care about OO? Because of all these great uselet frameworks back in the days. People were talking past each other for decades, and because I had products that are incommensurable, yet Lisp had it all in the 70s, so obviously they were compatible. And if I wrote this paper, if I'm talking today about that at LambdaConf or the LambdaConf seminar, because for 30 years I was confused. And I wish someone had written that paper that I wrote, or the one that I'm going to write to make it even simpler. So if there's something you don't understand, if there's a paper you wish someone had written, well, the solution is write it yourself. Okay, why are people so blind? Why does the industry care about correctness? Well, they don't care about correctness because for most problems in software, correctness does not pay the bill. It's much more work for less money, so it doesn't make sense unless you're writing medical software or avionics or aerospace or weapon systems. Then you should care. Academia, and so, but since most people in the industry don't care, most don't, and not developed enough in industry. FP is not developed enough in industry. Academia doesn't understand programming the large because most academics never write a program that is more than a few thousand lines of code, if they write programs at all. There are exceptions, not all exceptions, like Racket and other systems have lots and lots of lines of code. So obviously some academics understand some of programming the large, but most don't. And so that's why they neglect OO, because they think they can fit all the programs that matter in their head, but they can't. And at least real people for real programs can't. So we need OO programming modularly and incrementally. And both ignore the human factor because the industry wants cogs of interchangeable programmers, while the academia thinks they are gods. So both ignore the human factor. And all get stuck in their paradigms. And getting stuck in the paradigm can be great sometimes. I have this Douglas Hofstadter in the Tobod Marrow quote this great poem that I read out. Every task involves constraint. Solve the thing right complain. There are magic links and chains, forge loose and our rigid brains. Structures, strictures, so they bind, strangely liberate the mind. And indeed, if you set yourself within a set of constraints, wow, you find all the puzzles. It's like a puzzle to get the end, and you find new creative way of solving your problems by things or constraints. It's immensely liberating in a way to find new solutions to problems that sometimes you didn't know exist or sometimes existed by inhabiting constraints. But I have bad news for you if you say, oh yes, so it's okay to adopt the constraints of Haskell or whatever. But I have bad news, no. If you adopt the constraints of Haskell, you adopt constraints that great professors have adopted 20 years earlier, and they already picked all the low-hanging fruit. So by adopting the same set of constraints as your predecessors, basically they were liberated and they found lots of great stuff. By copying them stupidly, you'll find nothing new. You'll be just an idiot who inhabits constraints that others have already explored and that will lead you nowhere. So yes, you should totally find a paradigm, inhabit it, but do not just blindly inhabit the same constraints, same paradigm as others have done before you. And also be conscious that just because you choose one set of constraints doesn't mean that there are no other set of constraints that are just as productive as others. Just be humble. Like, yeah, be the god in your set of constraints, but recognize that there are other gods in other set of constraints somewhere else. So my meta-thesis is that there should be some amount of humility and not fanaticism when you find that, oh, we're functional programmers, therefore people who don't understand functional programming are idiots. No, they're not idiots. They have different set of constraints, and maybe they're inarticulate about it. Maybe they speak a foreign language and the language does not always make sense. But sometimes they don't make sense. Sometimes you are just the one who doesn't get the sense, and then you need to be more humble about it. If your paradigm is incommensurable with theirs, maybe the solution is not, well, sometimes the solution is just like ignore them, that's fine, ignore. But if you want to benefit from what they have to say, your solution is to go wider and try to understand what they have to say. And for all that, for going wider and try to understand things, that's where simplicity matters. And that's why I really enjoy having the language scheme, because I have all my lambdas and all my functional programming for the semantics and all the macros for the syntax. So at the end, my syntax is just as concise and just as nice as what I expect from object-oriented programming, and yet the semantic is just as nice as what I expect from functional programming. Okay, this is the end of my talk. I thank you for staying with me for 2 hours. I apologize for the issues with recording and with display of slides. Thank you so very much. The theoretical papers are at the URL displayed here. In practice, I implemented a object system based on these principles in Gerbil, the scheme implementation containing a Gerbil poo. I have an implementation in Nix, which is 30 lines of code or 80 lines of code with multiple inheritance. So these things take very little thing. If you want to add that to a language, pick a language that has lambdas and doesn't have object-oriented programming yet, and add object-oriented programming in a few tens of lines of code. My company is hiring sometimes when we have contracts, and otherwise when you don't have contracts, I'm for hire. So please hire me or be hired by me. Contact me at my email address.
And so, our quest comes to an end, with knowledge gained and bonds forged fast. The unicorn's light shall guide you home, as the legends of LambdaConf become your past. But fear not, brave heroes, for your journey continues, with new challenges to face and skills to hone. Until next time, when the unicorn calls, and the legends of LambdaConf beckon you home. For in this realm of code and wonder, your legend shall forever be sung.